Will you believe me if I say that I know a number to which adding 1 does absolutely nothing? Probably not. Well, let me show you something. I've written a small program to show you exactly that. Now, the output may not be very hard to guess here, but that's not the real question. The real question is, why is this happening? So, pause the video for a moment, think about it, and put your answer in the comments below. Congratulations to the ones who dared to comment. And as for others, what can I say? Better luck next time. Because the next thing that I'm going to show you is even more insane. Look at this number carefully. If you add 1 to this number, it gets incremented by 2. Now I want you to pause the video again and put down in the comment box that why is this happening. There's one thing that you may have noticed. In both of these examples, we are using float data types to store the numbers. Is this a strange behavior somehow related to the way floats store data? Well, it turns out that's the exact place where we find our answers. So let's dive in and see how computers deal with floats. Starting with a simple example. Consider this number. We usually read it as 12,345. But we can also write the same number in scientific notation, like this. Nothing has changed. We just have written the same number in a different form. Computers use exactly the same idea, except instead of powers of 10, they use powers of 2. So let's convert this number into binary. And this is its binary representation. Now, just like before, we can rewrite it in normalized form, but this time using powers of 2, like this. This form has two important parts. The digits after the leading one are called mantissa, and the power of 2 is called the exponent. In fact, every non-zero number can be written in this form. Now let's see how floats store these values. A float occupies 32 bits of memory. The first bit is the sign, 0 for positive numbers and 1 for negative numbers. The next 8 bits store the exponent, and the remaining 23 bits store the mantissa. Now let's focus on the exponent. Since we have 8 bits, we can represent 256 different bit patterns. You might think the computer simply stores the exponent directly, but it doesn't. Instead, floating point numbers follow IEEE 754 standard. And according to this standard, a number is represented as this, where S is the sign bit, M is the mantissa, and E is the exponent bits stored in the float. Now you might think that why are we subtracting 127 from here? Here's the hint. 127 is exactly halfway between 0 and 255. Pause the video for a moment and tell me in the comments that why do you think IEEE 754 does this? We'll come back to this a little while later. For now, let's get back to our original example. Our normalized binary representation was this. Now let's compare it with IEEE 754 format. The sign bit is 0 because the number is positive. The mantissa is simply all the bits after the leading one. If there are fewer than 23 bits, as in this case, we just append zeros until the mantissa field is full. Now let's determine the stored exponent. Comparing the two forms, we get this equation, which means E is equal to 140. Converting 140 to binary gives us this. And those are the 8 bits that will be stored in the exponent field. Putting everything together, this is what the memory looks like when storing 1, 2, 3, 4, 5 as a float. Okay, now that we know how floating point numbers are stored inside a computer, we are ready to answer the first question. Why adding 1677721 does absolutely nothing? Let's write this number in binary. If you observe carefully, you will notice that this number is exactly 2 raised to power 24. So its binary representation is simply 1 followed by 24 zeros. Now let's normalize it. The exponent is 24. So the stored exponent becomes 24 plus 127, that gives us 151, which easily fits inside 8-bit exponent field. So the exponent isn't the problem. The interesting part is the mantissa. Remember, the mantissa has room for only 23 bits. After the leading one, our number has 24 zeros. So, that means one of those bits simply cannot fit inside the mantissa and has to be discarded. But for this particular number, that's perfectly fine because the last discarded bit is 0. The value is still represented exactly. But now let's add 1. The number becomes this, and the binary representation of this number is this. And you see the last bit is now 1, which needs to be discarded. And if we discard it, it again becomes the same number as 167772216. So now you know that why adding 1 to 167772216 does nothing. But now you might say, okay, for the next number we looked at, adding 1 shouldn't change it either. So why does it increase by 2 instead? The answer to this is the computer isn't simply discarding the extra bits, it's rounding. By now you have probably noticed a pattern. From 2 raised to power 24 to 2 raised to power 25, only multiples of 2 can be represented exactly. From 2 raised to power 25 to 26, only the multiples of 4 can be represented, and so on. According to IEEE 754 standard, whenever the exact result of a calculation cannot be represented, it is rounded to the nearest representable floating point number. But what if the value lies exactly halfway between two representable numbers? In that case, IEEE 754 uses a special rule called round to nearest ties to even. Let's understand this rule with the same problematic number, 167772217. This number is halfway between these two representable numbers. Now just check the last bit of the mantissa of these two numbers. By last bit, I mean the 23rd bit from the binary point. And this number will round to the number which has this bit as 0. Hence, we can say that 167772217 will round to 167772216. Now let's take the other number for example, 167772219. Doing the same process again, you will get that this number will become 167772220. This also explains why 167772218 plus 1 becomes 167772220. Now the question is, why rounding this way? If you work it out further, you'll notice that the halfway values we are rounding up and down alternately, which helps to tackle the accumulation of errors. Now let's conclude the video by answering the question we left earlier. Why do we use a bias of 127 while storing the exponent? This is done in order to ensure that the stored exponent is always non-negative and it can be treated as a simple unsigned number, which makes the floating point hardware much simpler and faster. Now before you go, there are many interesting topics that we may explore here, such as how to derive the minimum and maximum values that a floating point variable can store, or why do computers use 2's complement to store signed numbers, or any other topic that you would like me to cover. Do let me know in the comments. If you enjoyed this video, do not forget to like, share and subscribe to the channel. And most importantly, do put your feedback in the comments. I am always looking to improve. Thanks for watching. I'll see you in the next one.